conference of this sort, being tested by the organizer whether my talk is ready, but it was...
And Marie will instead speak in mixed slot, which is Thursday morning at 10:15.
Allow me to... And I have a natural cut-off, so you shouldn't worry, because my butter will probably last 49 minutes, so I will not exceed the... Great. There's no... It's not automatic, it's just a laser here, I suppose. I just have to press the button, so... Okay. So it's really a pleasure for me, even being tested that my talk is ready at the last moment, to be here again. I thank Sabine for organizing this very, very interesting conference. And it's my second one in this series, and I really hope that things will continue on this. So what I'm going to talk about is actually related to what you heard this morning, and to probably slightly to what you heard in the previous talk by Xavier. Actually, I would like to define, to claim, actually, taking advantage of a given experimental GRB claims, what is a natural scale in quantum gravity. I'm discussing the naive naturalness here, so the starting point, before any normalization group running. So, this is important. Is this the Planck scale? Is this the string scale? What it is. I will try to... Why doesn't it move? Okay, good. So, I will try to review briefly what's the situation. This you all know, we heard in this conference, but I will be very brief. And I will try to concentrate a little bit on the Fermi results of this GRB 090510, with which I would try to tell you that this doesn't necessarily kill the models of quantum gravity by simply finding that the natural scale, if you are looking for modified dispersion relations, is higher than Planck mass. And this is because the Planck scale requires details of the microscopic model. In other words, to define what is a natural scale, you have to define what is your model. Like in the extra dimensions is a perfect case. Once you expand your dimensions, the Planck scale is not 10 to the 19 GeV, but you have the complicated expression with many parameters entering, like the volume of extra dimensions, times the fundamental string scale, and so on. And then I will describe very briefly a string theory model which essentially survives the above constraints, and in the context of which all these constraints of, if you find a time delay which is proportional to the energy, will essentially test the stringy uncertainty principle, I will claim. And that's why it goes beyond the effective field theory, because the uncertainty principle cannot simply be represented by adding local operators. There's nothing problematic with the theory of quantum gravity. It's just an uncertainty principle, and going beyond effective field theory, you will see what we mean. And I don't think I will have time, but I will describe also at the very end a bit of the contributions of this space-time foam to dark matter, for instance, thermal relics, from which you can derive constraints of collider constraints. So let me start with an old story very quickly. You all know, of course, the space-time may have even a non-commutative structure, or even Lorentz violating structure, where the gravity operates as a medium at scales, whatever the fundamental scale of quantum gravity is, and in which case, if it is a medium, then there is a refractive index, because the photon dispersion relation may be modified, and then there are hundreds of tests. This is actually a rather controversial subject in the sense that you don't have to have modified dispersion relation. For instance, in deformed special relativities, there are models in which you do not get modified dispersion relation. In low quantum gravity, also is not clear what is the state that you have to define. So, by looking experimentally at modified dispersion relation might not be the best way. However, I will try to disentangle a time delay, observed time delay in the arrival time of photons, from the dispersion relation in this part. And to do this, let me start with actually our version of dispersion relation, in which any modification in dispersion relation within a specific model may come by distorting the metric of space-time in a way so as not, the induced metric does not depend only on the coordinates, which I haven't written here, but it depends also on the momentum. This is a Finsler type. Actually, in mathematical terms, Finsler is something more, requires some homogeneity and some color structure in the metric. But these are the metrics that I'm going to talk about. And this is the dispersion relation of photons in such a disturbed metric. This metric is induced by the interactions, let's say, with the phone. And we have two, in my research I consider two terms. One is the most naive term that you can think of, which is a coordinate dependent. I have to stress that when you're looking at dispersion relations, when you're measuring refractive indices, you're measuring velocities. So it's a coordinate dependent issue, okay? You have to relate things to proper time, and so that the effect is there, but when you're measuring something, when you're measuring a speed of a refractive index, you're always fixing the frame. And for instance, one particular case is when you interact with the defect in space-time, and the defect recoils, so to conserve momentum, you have a momentum transfer. And if, for instance, in this particular case of string theory, this is plays the role of a bare Planck scale, the string scale over the string coupling, and this sort of metric just represents the metric in a boosted frame with Galilean velocity ui. Actually, you could either have the Lorentz factor here, and it could be two orders. That's one type. The other type is quadratic. It's like this. The other type that I'm going to discuss, in particular in context with this model, has this interesting feature along the direction of recoil with the defect, because the defects represent space-time form here. You have a metric which becomes singular when the recoil velocity approaches the speed of light. It's always subliminal. And this actually introduces, as we shall see, a higher order cutoff, like the GZK cutoff, as a result of Lorentz invariance in this implicit way. So
what is delta K?
Pardon?
I want to really understand what you're doing. What is delta K?
I will explain, but that's is the momentum of when you have a defect in space-time, you will see, and you have a photon interacting with the defect recoils so as to conserve momentum, and delta K is the momentum transfer of the photon before the scattering from the photon after the scattering.
Okay, how in the green you have a metric on momentum space.
There, that's right.
Is a function of P.
I will explain how this comes.
That P is not related to that delta K.
No, delta K is, if delta K can be parameterized, as you will see later on. I mean, since you asked the question, I can skip a few. Okay. Since you asked the question, I will answer it now and then I go back. You see, I can parameterize delta K with a fraction of the incident momentum, which is the P of the particle. So it's a momentum transfer. It's P prime. The K should have been P, actually. It should have been delta P. But I defined a wave vector. You know, I distinguish between momentum and wave vectors. But delta P is a fraction of the momentum of the incident photon.
All these,
No, a stochastically fluctuating one.
all this is in the rest frame of the defect. All this is in the rest frame.
All this is in the rest frame of the defect. So that's why it drags the frame. So in other words, you are in a comoving frame with a defect. And that's why it's a coordinate dependent thing. That's why this metric is. So this is actually, because in the way, when you will see later on when I describe in detail this interaction, that's how we describe in using a sigma model in string theory. You have to be in the rest frame of the defect. So is that defines what I thank you. And you see here, coming back to Lee's question, it's fluctuating, and on average the fraction is 0, but you may have stochastic fluctuations. So you may have Lorentz invariance on average, but not through its fluctuation. So the U squared in quadratic terms should lead to non-trivial effects. So this is the type of dispersion relations I'm talking about, but in a model-independent way, if you want to measure this sort of dispersion relations, you actually have to measure refractive indices. If you have this sort of situation, or any other kind of situation of modified dispersion relation, for instance, you may have a modified dispersion relation in the way the deformed or doubly special relativity community is doing, by not having an induced metric necessarily, but arising from the certain assumptions that you put in your axions in the theory. Or maybe in certain cases these two are equivalent, it depends on the type. Once you have this, the phase velocity and the group velocity of particles or waves are not the same, and you define a refractive index which is a function of the momentum or the wave vector k, if you like. And you then have superluminal or subluminal waves. So this is actually an artistic version of this thing. Green is the high energy, so it would arrive later. Upon entering, I deliberately have the densities of the foam here different, because in general it may not be homogeneous. And we have heard from Robert this morning that the emission mechanism is essential because the observed delays that you see might be due to standard astrophysics. So you have to disentangle this. And the only way to disentangle this is to have a lot of statistics so as the propagation effects are disentangled from the source. So if you see, for instance, consistent delays over 2,000 or 3,000 events, then this is unlikely, well, unless there is a specific mechanism for the AGNs all the same. So that's what we, and if you have subluminal, as it is the case that I'm going to discuss here, the higher energy photons will arrive later. However, you may have another effect of quantum gravity, and since I'm taking the opportunity of mentioning, and I'm sure we will hear more, it may be stochastic fluctuations. You may have, on average, you may have, let's describe stochastic fluctuations, which have been first suggested by Ford in 1994, and then elaborated by Hugh and Ford and other collaborators later on. You may have a modification of the, let's say, Minkowski background by an HV nu which is such that on average the metric is flat, but when you consider correlations of this graviton state are non-zero. And it depends what your graviton is here. You may have coherent state of gravitons, or you may have all these stochastic events with space-time that I was talking about. In this particular case, again you measure an arrival time of photons, but there you have some photons that propagate faster than light, others that propagate less than light, because it's a stochastic fluctuation, it's an uncertainty in the arrival time. This is a coordinate-dependent expression. However, you can show that this renormalized fluctuation, in other words, you subtract from here the flat Minkowski space-time infinities, is related to the geodesic deviation, and this is related to the curvature, and we all know that in linearized gravity the curvature is independent of the gauge choice, because once you modify the gravity with an HV nu, then the coordinate changes here are the gauge fixing the gauge freedom is lost in the curvature. So this is an actual effect. And these sort of fluctuations may depend on energy, and they do in fact in this particular model that I was discussing, with this delta p, if you like, the momentum vector, because you may have the stochastic fluctuation of many things, in particular of the d particle itself, because it's a string theory and it does precisely this. So this stochastic fluctuation may average in zero. The momentum transfer actually during the scattering might be fluctuating, might not be fixed, and only stochastic fluctuations could be non-zero, and that is actually one particular case. And what you're going to measure in this particular case is not a delay in the peak, but you would measure an energy dependence of the width. And in this particular case, that's an independent phenomenon. It might be much more suppressed because the stochastic fluctuations come, for instance, in the case of string theory, suppressed by higher powers. But you will see, in this particular case, the width actually increases with the energy. And you see that lower energy have more sharp, the lines, the spectral lines are sharper than the higher energy ones. So in this particular case, you measure the same photon, the same spectral line, but you look for at various energy channels, and you look for the energy dependence. This effect, if it is there, is actually independent of the source, right? I mean, because it would be a rather, well, okay, independent is a big word, you don't know the emission, but it would be rather unlikely that the line broadening would depend on the energy at the emission of the source. So that is probably unambiguous if it is seen. Unfortunately, it is harder to see. But that's also another thing that the astrophysicists could do. They should look at the broadening, the energy dependence of the broadening of the spectral lines. So this is more or less what the situation is.
So
yes.
Will it depend on the redshift?
Pardon? It will depend on the redshift. I will show you. Yeah, and that's why it makes it more. Well, actually, the time arrival will increase with the redshift because it will be like 1 plus z. Okay.
But in addition, for example, if this was just a Minkowski space-time
yeah.
model, actually a Friedman model.
Yeah. That depends even on the cosmological model. You will see later on when I show you there. So that complicates actually all these uncertainties. That's why, and it depends also on your cosmology. It depends on the amount of dark matter available. It depends on the type of cosmological model, because it depends on the Hubble parameter, and therefore that carries information.
It's like a dynamic equation for...
Yeah, the whole thing, it's highly model dependent. So that's actually the message I want to stress, that you have to be very, very careful to disentangle things. You will see, for instance, at the end, what particular dependence we're talking about in one particular model, not in general. But that's all. In fact, any model, if you come up with a new cosmology, these are also if it is space-time foamy type, in other words, if it introduces a medium over which photon propagates, you should consider all these effects. So the effective field theory, I won't describe much here. I will just skip it. I have actually one comment to mention here. If you want to describe these effects in an effective field theory, we had discussions, you add these coefficients, and there might be a caution. There might be, from what I'm saying, it might be that the average of these fluctuations of Kosterlevsky and other are zero, and only the fluctuations are not zero. So the average of the quantities, sigma, A, B, or whatever, may be zero, and therefore maybe the effects actually may be much more suppressed. So that's the only thing I'm going to say for this. I'm not going to discuss this. So we have said also the three astronomies that you look. If you're looking at effects of space-time foam, in general, you would expect that the space-time foam would act universally. That's not actually the case. In string theory, because of charge conservation, we will see that only neutral matter can interact. But in general, these are the three astronomies that you do. The gammas, the protons, which are bad because they're deflected, and the neutrinos, which is one of the best. But, of course, the price you pay is that the cross-sections are very small. But these are leptons, and they propagate over large distances. And we have had interesting talks by Dr. Kelly this morning on this astronomy. So this is the cosmic photon. I mean, it's just a very quick caution actually on what you are looking at. There are three things that you have to be careful once you try to interpret a delayed arrival. If you measure arrival times, so as to test this stochastic fluctuation or foam models that I talked about, you have first of all to know the uncertainty. You have to resolve the emission mechanism or accumulate statistically significant populations of events. But even if you have this, it doesn't necessarily mean that your effect would be due to quantum gravity if it has birefringence. Birefringence means that the time delay depends on the polarization of the photon. If you have such a thing, then there are very, very stringent constraints from even photons that kill, for instance, linear modified dispersion. So you need a model that does not have birefringence, and this is actually the deformed or W. What is the status now? What's your preferred name for the DSR? W or deformed, I would say, isn't it?
No, but does not have birefringence.
No, I know. I mean, your name, how do you call the DSR now? What's the preferred deformed? Yeah, so that's what I'm asking.
You just said DSR. Doesn't matter what
DSR, all right. DSR do not have birefringence, and that's what I was ready to say. This is actually yes.
Well, why are you raising? I mean, generically, they don't expect anything that is Lorentz invariant violation to predict birefringence.
With an effective field theory, yes. Yeah. So it depends. With an effective field theory, it's generic.
It is CPT violating as well.
Yeah.
5 operator.
And you will see how. But this is not in our case. You will see because it's not effective. Yeah.
Just to say that, however, that the best constraint now are with the Crab nebula as well.
Yeah, I will come to.
From birefringence.
Yeah.
Not from.
No, not from electrons. I have the photons. I have the transparency on this, and I'm just. That's what I put here. Photon test on birefringence and massive things on the difference.
No, the photon test on birefringence are coming from the Crab nebula.
Yes, that's what I mean. But I put it. That's what I'm saying. This comes from the Crab nebula on the photon side. That's what I said. You should not have them. They're both. You'll see. And then there are ultra high energy cosmic rays, which I will say a little bit more. And if you have the GZK cutoff, actually, what I mentioned earlier for this metric is important. Because if you notice, I have mentioned this type of metrics that you can get. And you see, this acts as a cutoff. If the momentum transfer, which is a fraction of the momentum, is less than the speed of light, that means that if the momentum fraction is ms over gs over r, if the momentum, this introduces a new kind of cutoff of GZK cutoff, which might be of the order depending on the strength scale. So that's another constraint that you have to get. So I will cover, okay, here is the, fine. So this is the photon test on that side. These are the other massive, if gravity is universal. It's actually quite beautiful that we can really test models. I mean, to me, a good theoretical model is a model that is falsified immediately by experiment, right? That's the definition of a good model. Right? Because A, it doesn't cost much, because the experiment is already there, it was built for another purpose, and you falsify your model and you say, fine, that's a physical model. Most of these tests actually are cost-free, in the sense that the experiments have been built for a different purpose, all right? And you only have to modify your Monte Carlos to include this effect. It doesn't cost that much. So it's a user-friendly, environmentally friendly, and financial times friendly method. But maybe content-free as well, in the sense that it may only divide bound, so you would rather hope to get some signals eventually. The other thing is we heard this morning is decoherence effects, which is another feature where on average the Lorentz violation might be zero, might be averaged out, but you have stochastic fluctuations and you can decohere. And in this case, probability, this is, I mean, here there is one that constant depending on what probability you're talking about, but the important point is that the oscillation probability is modified. Actually, there is more modifications here. You also shift the phase of the oscillations, but it's not important. The important point is that there is a decoherence coefficient. This is model dependent. The form of the energy dependence of the decoherence coefficient in the oscillation probability is model dependent. The time, the power of the time is model dependent. In any case, that's what you get. You get always what is model independent is that the coefficient is less than 1 if you have decoherence. And a third one, which unfortunately I won't have actually time even to mention, is that if you have a space-time form, which is of the order that, let's say, magic result has measured today, because magic has looked at HGNs at redshift 1.3, almost today, then this space-time form may affect, in fact, as a result of each quantum fluctuations, EPR correlations between, let's say, neutral chaos in Kerr factors. That's CPT violating effects, but that's a different thing. So, briefly what I said early, I mean, exploiting the fact, I was not planning to discuss this, but since I talked today, I decided to adopt quickly my talk to this. The massive, if you test massive probes, then the best constraints come from synchrotron radiation from the electron spectrum of Crab Nebula, as was discussed by Jacobson, Liberati, and Mattingly long ago. And then there was a question this morning, I think by Thomas, asking what's happening with quadratic suppression. Actually, we will see that you are very close, you see, to quadratic for synchrotron. You've already excluded the linear, and the A is bigger than 1.74, and I think this number is pretty close to 2. So you see, synchrotron radiation is very close to excluding for massive probes, for charged probes, but not for photons. So for photons, okay, that I skipped because you heard. For photons, these are the evidence of delayed arrivals at the moment. Magic, the first one, which was a paradigm shift at the time, I must say, because they were the first who observed the delayed arrivals at TeV. And they observe a order 4 minutes. Actually, if you do the analysis more carefully, it's about a minute, what you actually mean. The Hess, originally they claim no observed time lags, but eventually you will see the limits. Then the Fermi, they started observing GeV immediately within the first year of operation. So this and this have been derived with, they observed time delays of order 82 seconds, so it was too weak to do any sensible constraints. And energy is 13 GeV or 33 GeV. That's the highest, actually, GRD ever observed so far. But they've been lucky, and they've observed at a redshift 0.9, which notice is the redshift from that corresponds to the passage from deceleration to acceleration of the universe, right? And they have observed the highest energy photon 31 GeV or 10 photons in the regime of 1 to 10 GeV, which were delayed by less than a second from a very short and dense gamma ray burst. And that is enough to, if you plug it in naively in your, that's right, if you plug it in naively in your formula, is enough to get constraints higher than the Planck mass. So that's the question. I leave aside the delayed arrivals, that's how to disentangle. And I'm concentrating on this. So that's the fit. All the other 4 that I talked, if it is fundamental physics and the delay is linear to the energy, you can fit them. Even the hash here, just in the border, and that's the magic actually. So it's the error is inside. That's the theoretical error. But that's the redshift as well. You see here that the cosmology details matter here. If you change the energy budget, you change the thing. But that's the Fermi, and that's what in the next 10 minutes I will very briefly concentrate and take a few minutes for my question time.
Can you slow down?
Pardon?
The line you're claiming is fitting is what?
This is from a linear fit, taking into account the errors given. This is the best fit in the models, taking into account theoretical uncertainties.
What quantum gravity?
Nothing at the moment. It's just delta T over energy. It's a linear. It's the only thing that I took a linear dispersion relation. The only thing that I took into account is the cosmology.
Wait a second, 0.4, I think you have factorizing.
Sorry, you talked about what value we got. Yes.
Psi equals 0.4.
Sorry, the magic. Sorry, if that's what you're asking, yes. I thought what model of quantum gravity was. Yeah, it's the Planck 10 to the 19, 10 to the 18. Actually, the magic 0.4 is close to 10 to the 19.
You can give it
No, but it matters. It matters. That's the point of view.
Oh, of course it matters. Yeah.
So it's 10 to the 18, not 10 to the
10 to the 18, not 10 to the 19. It's the magic. 4 times.
Right. So
it's here. It's yeah.
That's the
So that's the 4 could be fitted with the magic, which is 10 to the 18 point, 10 to the 18 GeV.
Right. Okay. And now, but the Fermi.
The Planck
The Fermi is in disagreement.
is this with a 1.5 10 to the 19.
That's the Fermi.
That's the Fermi.
Right.
That's the 0.9. That's what I'm gonna discuss now. So naively, you say fine. I killed the thing. All right. I mean, it's unnatural. It's higher than the Planck, and everything is
It's
fine.
not higher than the Planck. 1.5 is not
Yeah.
higher than. It's at.
Yeah.
But it killed.
I absolutely agree. Yeah. If you
But it is in vast disagreement with your claim.
is in vast disagreement with the magic. Let me put it this way.
The claim is surely not sufficient to
Yeah,
run
the constraint as it stands, I would say fine, the magic has a big ingredient of source events, and because the Fermi, which is a short burst and is most likely more sensitive to quantum gravity, maybe that's the Planck and everything was fine. I absolutely agree.
Yeah, but is the issue that the experiments are inconsistent with each other, or is it that you're forming
No, of course.
the experiments?
They are different experiments, first of all, right? They are different experiments. So a combination of different experiments. So, but at the moment as a theorist, you have to do something to even see, let me explain that. You know what I mean?
It's going to explain why they are not
If you say
Hope you're
it's
counting this for my
impossible,
question time.
Yeah.
Sorry?
Now he's
you
going to
could say
say
how the theory is possible, and then you fit them.
No, but then the talk is here. Then there's no problem, and thank you very much. So it's up to you whether you want to hear the rest or not. I agree. For me, the claim, you see, you read the claims of Fermi, okay? If you read the claims of Fermi, then we should all go home. We shouldn't even look
But
for
Nick, there's another question. The claims of Fermi are limits, and you have them as observations. Like the 09092b was published as a limit, not as an observation.
in the published version. Yeah, but that's what
So it goes down.
it's bigger. That's what they did. In fact,
No, it goes down. It doesn't. It's not the error bars around that value. It goes down. It's a limit, not a measurement.
oh yeah, but that's what I mean. The M2G.
No, not the one in the box. The Fermi GRB.
Oh, sorry, yes.
You
Yeah.
have that as if it were a measurement, but it's a limit. They published a limit, not a measurement.
Yeah, fine. But that's the paper version, which is the nature version was different from the one in the archive.
You're talking about the one on the top.
Yeah, that's not a measurement. That's a value.
Sorry, what are you talking about?
He's talking about the one at the top.
Oh, the 09 you're talking about, not the okay, sorry. Yeah, I agree.
They're all. I mean, Fermi has only published limits. They have not published an observation.
Yeah.
Sorry, I am completely lost. What is going on here? Can somebody explain what is the issue?
I can say it. No, please go ahead.
Okay.
Sorry.
Fermi, I mean, my point of Fermi claimed that they observed a short burst where, as I said, earlier than they had 10 photons, 10 photons between 1 and 10 GeV, and 1 photon of 31 GeV. And it arrived later, the 10 GeV and the 31 GeV, it arrived later than the MEV and the KeV photons by half a second. And the best was extremely short as well, 0.49 seconds in duration. So they claim that because if you try to fit this measurement to the formula of the magic, which was 10 to the 18 GeV, in order to fit these lines, then you are in disagreement. So the quantum gravity was unnatural. That's what they say. And what I'm going to claim in the remaining minus 2 minutes, but plus my question time, I will count it plus 95 minutes. Plus or minus is an error. It's not a measurement yet. I will try to claim that through an example, which is actually quite indicative and solves other problems, that you have to be very careful. Even if you take at best value, I can still reconcile this measurements, well, up to here, which are at low redshift, 0.1 and 0.1, with this by, and this you can reconcile actually with these 4 points, you can reconcile everything if you assume, naively, that the density of defects of the space-time form that I'm going to discuss is not uniform. Or you can, so in other words, I will claim that 4 measurements are not sufficient to really rule out any hope for stochastic fluctuations or whatever. First, because of what Lee has already said, we redone the analysis. Originally Fermi claimed in their published version that there were analyses if you do with 100 times the Planck, but that's wrong. The only limit that you can get is 1.5 and actually 1.22 if you take more of the public data recently, and that is at the Planck. And the second is that the uncertainties in the method do not give you. So, remember, now let me ask the question, is there a model which you can fit these delays, including the Fermi, and whether it's sufficient by just the arrival times, even if the fits are okay, to claim that they are sensible from the point of view of modified dispersion relations or Lorentz matrix? The answer is, first of all, no. First of all, you have to have no birefringence, because here is the birefringence constraints, which Stefan was talking about, and they've improved even later on this, and you see that any generic effective field theory has birefringence, because you can write it down, when you write down the dispersion relations, that's the quantum gravity scale, is plus or minus. So within the effective field theory, you cannot have it. Now, the ultra high energy photons as well, by the fact that you don't see very high energy photons, otherwise that you don't see photons above your GZK cutoff, again, you can easily constrain the model. Superluminal propagation here cannot be constrained. That's another important feature. So superluminal or stochastic fluctuations you cannot constrain. Or quadratic effects, as I was talking about the U-square. Quadratic cannot in the dispersion relation. So let me see what we do. So I will argue in the last, I have 5 minutes, that the time delays are proportional to the energy, but they are going beyond the effective field theory because they describe uncertainty. So the dispersion relation in the model I'm going to talk about is quadratic, is the one with this minus u squared. And you may have possibly z-dependent effects. So this is the important point that I want to specify here. You have to disentangle the linear time delays, even if they are observed, from modified dispersion relation. And that goes beyond effective field theory. So that's the model. If you could see 2 colliding brains, Randall syndrome, it heats up, it becomes red, it hits the universe, then if you could see eventually formation of stars, and you have open strings propagating on the left or on the right from the brain, and they interact with the defect. That's the model. And during the interaction, this defect recoils, and it has energy momentum, and it has modified dispersion relation because it has momentum transfer. So what is happening in pictures, because you can describe it using string theory scattering here, you have a non-local state, a string state emitted. This is the brain, this is the cross-section of the D3 brain. It's emitted, and it oscillates back and forth, because this end of the string moves with the speed of light on the brain. So the Lorentz invariance is fine as far as string theory is concerned. Forget about the types of string theories, we have various defects. But the important point is that because of this brain, if you like, the defect cuts the string, the electric charge has to be conserved. So depending if it is, depending on the type of string theory, you have type 1 2A string theory, which accepts the 0 point-like brains. the electric flux has to be conserved, and therefore the only interactions that are allowed are those of neutral particles. For type 2b, you can show that type 2b includes convectified defects, which still look point-like, but they have a small diameter, and there you may have a little bit of charge here, but then the charge dispersion relations are suppressed. So there's a non-universal action in this particular model between photons and electrons, and that's the important point, remember. So that's what I have to say. So the Crab nebula for electrons do not apply here. Then, forget about the string. This is transparencies that I was not planning to show. Doesn't matter. It's important how you compute them. You compute the amplitudes, actually, I'll tell you, because these are uncertain. So it's okay. If I can take... What I'm supposed with the questions? 3:30?
Yeah, so you have 5 minutes.
That's fine, that's fine. I mean, I have questions and I can discuss people if you like, so it's okay. So, the interactions are like this. Open strings split. You have 2 open strings coming, 2 open strings leaving, and the d particle recoils in between. You can do it using string amplitudes, never mind about that. The important point that you have to notice is phases. When you have string amplitudes, you look at backward scattering, u equals 0 in the Mandelstam variable. This has nothing to do with the recoil velocity, and you look at scattering, phases in the amplitude. And the phases are always the S, which is the total energy squared, times alpha prime, this fundamental string length. So the phases induce delays, because think of plane waves. You have plane waves plus a phase, which is the energy times delta t. So the phases induce delays. The delays are energy proportional to the energy. So here, careful, there is nothing and independent of polarization. So here, I've done nothing on the dispersion relation, right? I mean, I have a string, which has a standard locally, has the same dispersion relation as the one dictated by special relativity, but I still get a delay. And the delay is because of an uncertainty, okay? The delay, you can estimate it and you can show. For instance, you can assume that you have an energy P0, which then the string oscillates, does a number of oscillations, and the energy is conserved, and this causes, taking into account the causal nature of the delay, which happens only in string theory, and you have that the delta t is proportional to the energy. And that's the point. No birefringence and a delay. But if you have many defects, a number of them effective interaction and star, including the possibility of interaction with the cross-section, you see that the delay is proportional to the density. So if you have no defect, there is no delay. If you have very rare defects, you have very small delay. So you see the effective scale, if you include actually, the effective scale depends on the effective number of defects encountered. And if you include the expansion of the universe, this is what you get. And you get an effective gravity scale, which is not the string scale or the Planck scale. It depends on the details, how many brains defects you have in the model, right? And that could be redshift dependent. If it is redshift dependent, that's actually the effective scale. So in other words, it is proportional to the probability of interaction, which includes the cross-section, and you can estimate what this is the linear scale. And you can have a homogeneous bulk, for instance. You may have a concentration as this propagates in cosmological times. You may have thicker events here or later on, and that's what you could account for this event. So that's what I mean, that's what takes into account this fit. So you may have actually a situation in which the density of defects is of order 1 per Planck length in the low redshift area, in the redshift where we have acceleration of the universe, below 0.9, but for some reason you may have a void of defects. And in this picture, it's totally natural. The one that I told you, there's nothing to tell you in string theory what is in between, whether you have a void as it propagates or not. This is only a toy model. I just wanted to demonstrate how is it possible to get a string scale not depending on only on MS, an effective quantum scale, but depending on defects of the model. So these are compatible with the string uncertainties, delta t, delta x, and I'm finishing in the remaining 2 minutes by pointing out that in string theory, and that's in any theory that has non-local objects, you have an uncertainty between time and space, and this uncertainty is compatible with this action. And that's why it goes beyond effective field theory. Why? Because in string theory, the recoil of the defect, for those who are experts, can be described like this can be described as a B field, which is proportional to this momentum transfer. Already having a momentum transfer is a non-local operator. But then, this induces a non-commutativity in space and time, if you have a strings in a background fields which is momentum dependent. And this non-commutativity introduces a metric, which you calculated by looking at correlations, doesn't matter. It introduces a metric of the type that, notice, is quadratic. So that's the difference. The delay that you computed by this scattering is linear, delta t is linear in energy, but the dispersion relation is u squared, and u is quadratic.
What's theta mu?
Theta mu is the commutativity, it's this. Oops. 0I, theta 10 is the delay, is this parameter. The delay over 1 minus u squared. It's the B0, it's theta 10, only 0, so this is the recoil velocity. So having the recoil velocity induces both space-time non-commutativity and this quadratic dispersion. And, most importantly, the effective string coupling becomes proportional to this factor. So when u is 1, that's the important point, and I finish. When u is 1, because u is momentum transfer over the string scale, then you have a new type of cutoff. First of all, the first thing that you have to remember is that the dispersion relation is quadratic, although the delta t is linear, so the string ascendants go beyond what you would call a local field theory. And the second is that you have a new type here of GZK cutoff, of a high energy cutoff, when the momentum transfer is of the order of this 2G, which is ms, over the string coupling. And this is a free parameter in string theory. It could be TV, could be whatever. So you can constrain with this model, taking into account the density of defects, you can constrain the model and avoid this high energy constraint, because now you have a UK cutoff. So this is what I wanted to say. Forget about the other effects. And I would like to conclude by, okay, the conclusions I'm not gonna, the outlook is what is important, and that's what I finished. The outlook is a complementary constraint. Once you're talking about space-time foam, you have to think about cosmology. You have to think about dark matter as well. You have defects. They operate as dark energy, because these are localized defects. Yeah, that's an important point for string theory. These are localized defects. So you may naively think that you can use them as excitation from the vacuum. All right? Any localized effect, it's one way. It's not, because if they are excitations of the vacuum at very heavy scales, like ms over gs at 10 to the 18 GeV, may be washed out by inflation. So these are the only excitations that you look are contributions, they're fluctuations. That's the only thing you see. And their stochastic fluctuations lead to metric. When you embed this metric in the Robertson-Walker expanding universe, with this stochastic fluctuation you get metrics like this, and you get a Boltzmann equation, let's say, for thermal dark products. This is just an outlook that has a source. These fluctuations act as particle production. And a particle production in the Boltzmann equation for determining the Rayleigh abundances acts as sources. And it affects the Rayleigh abundance by these terms. Right? So you see, sigma square is the fluctuation, delta square, in fact, is the energy. This sigma square is energy square. And you get this sort of correction, which actually you can constrain them. Some of them, so depending on the density of foam, you can constrain in order to have acceptable cosmologies. You can actually constrain them in an independent way like this. So I would like to finish. I finished, and I'm not going to exceed my time, so I will accept only one question. What I will have to say is that on the experimental side, the increase of statistics in astrophysics is essential, like in any experiments, because that would help you really disentangle source effects from whatever effects you have and from the model purpose. Because before events, you can't say much. Thank you very much.
So the calculation of the fluctuation of electrons by Ford, you and others, maybe I missed this, but how did you use this calculation in your analysis? Or
Not
just
in the...
motivation?
Yeah. Here I use it, for instance, in the last transparency, in the I use it like this. The average of the G mu is 0, is eta mu, and this gives me the sigma square, the fluctuations of the sigma square.
Okay, but that's not the result predicted by the calculation by
No.
This
This is within this specific model. The calculation by Ford, I used it, if that's what because in this model that's how I use it. But in the Ford, you just measure the arrival times of a single photon, and you look at the width of the pulse.
Okay, so they're just the same observable.
Yeah, it's the same observable, the same photon, but in different. So you look at spectral lines at different energies, and you look at their pulse broadening. And if it is energy depending on the model, you will. So that's the.
In a consistent way, basically, now I'm getting confused, but regarding the evolution of, or if you want, the different routes that took your model in time, because you had an early version with the one on which we based our analysis for the constraints based on gamma-gamma interaction, phase production,
Yeah.
in which you were computing basically the photon per production. While in this later model you say basically that you cannot apply that analysis.
Because
but the model you had recoils on the
Yeah.
particles. And I don't
but the
understand-
average was not 0 in that model. So it was UI. That's what I'm trying to find.
Right, but but in your paper you think of a third way. You say that there are basically three ways you can escape, evade our constraints. One is that the UI doesn't have an average just average to zero.
Precisely.
That would be the same model as you did in 2001, but simply that is isotropic on average.
That's right.
Okay? But then you say that there is this other model where you have these strings that excite and then relax. And I don't understand why in this model...
That's not different actually from the stochastic. In this model, that's actually any generic string scattering involving an exchange of an intermediate string state. So, the only thing which... This is just probing the uncertainty, if you like, of that regime. So...
But I don't know, because in the 2001 models you had, you were modifying the dispersion relation and adding a term to the conservation of energy to take into account
That's
the
right.
points.
But
But
which
here
was...
you're not, you're saying you get the time the delay without modifying the
Yeah,
dispersion
because I
relation.
did the detailed calculation within string theory, which we haven't done in the model of in the earlier models that we were. In the earlier model was phenomenological. We added the model by hand for the energy conservation. Here the energy is exactly conserved. You see what I mean? And the only thing that you probe is just the uncertainty. So there's nothing... Here is standard string theory scattering with this defect. So nothing you don't... And the only the only thing that you take into account is this recoil of the... I mean, we can discuss. I'm happy to discuss in detail because probably... But this is what we haven't taken into account in the previous model. This, that you can, in the string calculation, that's critical. You see, first of all, there are two models. One was the non-critical string, which you're referring to in the other model, where we dressed the situation because we took into account the non-conformal nature. But I don't know probably if that's the appropriate model. But here we just took standard string theory calculation. We've done nothing else. That's the only thing we observed. That's the recoil of the particle expressed as a modification of the boundary condition in the worksheet, amounts to having a background phase, locally. That's what breaks locally the Lorentz imbalance, and on average is it.
Can I make just a comment? I think that there is a danger in a certain sense in this kind of model, because it is becoming a model where you can basically constrain it just with the time of flight. And I wouldn't, you know, in a certain sense, I would like a model that can be, if you want to define and make a claim, you have to constrain it.
But the model of this has the following advantage. The dispersion relation is quadratic. You see, there is an induced dispersion relation, but it's U squared. So you cannot constrain it.
Why? With the high energy, ultra high energy.
Oh, yeah, with the high energy you can, but...
Stefano, gamma going in plus minus.
Stefano, maybe you can discuss this in the coffee break, and let's say leave something.
Yeah, you make things very complicated. Let me make a very simple statement. Okay, from the point of view of phenomenology, okay, we have been trying to understand if there is an effect where the speed of light depends on energy, where there is one formula. Okay, the speed of the photon is c times 1 minus the energy over some
Fine.
Quantum gravity scale. Okay. The MAGIC collaboration claims to have made a measurement of that M quantum gravity of roughly 10 to the 18 GeV. The Fermi experiment puts a bound which,
A lower bound.
which eliminates that.
That's right. Oh, but not.
So there is
That's the
zeroth
phenomenology.
order, no. Zeroth order. There is a disagreement
Sure.
between the claimed observation of MAGIC and the
Sure.
claimed observation
Sure.
of Fermi.
Sure.
That's the zeroth order.
That's the zeroth order. But I claim that the scale that enters your delta C, if you like, the correction to the speed of light, the refractive index. The refractive index is a cosmological era-dependent object.
But
You are
Before-
assuming
before
there is a
you-
deep perception.
There is a void. There is a deep.
no, but look, we're free. We theorists are free to play any kind of games where we
Yeah.
invent things like voids and gases and defects and so forth. But let's be honest, we could get anything the experimentalists see in any data by inventing voids
Yes.
and defects of objects. We get
No, but-
anything at all. So
No.
why is the use of making that claim? You could get in different directions.
No, I
different-
disagree completely. So I'm sorry, I completely disagree because if you don't believe the magic, then fine. If you believe that the magic has nothing to do with fundamental physics, then that's fine. I mean, then it's astrophysics, which I also believe it is, and there's nothing to talk about. You know what I mean? I mean, in this context. But if you believe,
No, what I'd like to hear from the side of the observers, not us theorists, we can make stuff up.
Side of the
What I'd like to
observer-
hear from the side of the observers
Like
is
you heard, these are the numbers.
is there an experimental reason to trust more one of these observations or the other, just from the experimental side?
I mean, the experimental, well,
Because there is a disagreement.
but the disagreement is,
No, but before we make up theoretical games, let's try to understand.
but there's no disagreement. That's what if you, from the experimental side, there are two observations. The magic claims that they observe delays.
On the simplest assumption that we're already making a radical assumption in this field, light might depend on energy. Sorry about that. On the simplest assumption that formula is worth studying, there are two different measurements, and we should. It seems to me before we theorists play games, we should understand from the observers how serious is that disagreement. How many sigma is it? Where are the weak points of the
Well,
observation? I'm just wondering, maybe some of the observers could comment.
It's only one. It's only one measurement of Fermi. Yeah? So it's 2 sigma or something.
The
Right?
issue is not going to be there, but the formal error bar is statistical.
Yeah. It's only you only have 4 data at the moment of delayed arrivals, nothing else. 4 points. So in principle, you don't even care. That's what I say. You have to accumulate much more statistics before you do things.
I think that you are careful with systematic. Which is a different issue.
Sure. And there are different experiments, first of all. There are different experiments.
Different sizes. So there's going to be different
But I'm not the appropriate person to comment on that. We have to ask Robert or even someone from Fermi as well, because there are different experiments. However, I claim that the observation of the arrival times, Fermi, if you accept the bound they put in, higher than 1.5 times 10 to the 19.
1.2.
Sorry?
What was published was 1.2.
No.
What
1.2 was one of them. They have various things.
1.2.
Yeah.
1.2
That's fine.
the claim in the nature.
That's fine.
Let's stick to that.
I know. Okay, 1.2 10 to the 19 is the bound of Fermi.
Right.
And the bound of magic is clearly 10 to the 18 GeV order. Actually, 0.4 times 10 to the
As
19.
bounds, they're consistent, of course.
course.
But the magic paper made it leap claim of
No.
detection.
We also know, no, absolutely not. The bound. Yeah, I think Robert is there.
This delay can be perfectly explained by source intrinsic mechanisms, and magic was aware of that, and there is no claim that we can rule out source intrinsic mechanisms.
Here.
So that's the most.
And I've shown in my
Here.
talk 3 mechanisms which perfectly
Sure.
explain how this
Okay.
can come about.
So
Here, Lee, I also mentioned here, you see, there are modified the SSC, and in fact, Robert has talked
What is
about the time
SSC?
delay, which is inversion.
So-
SSC is not your, it's substitute on Compton
So
here.
the prudent interpretation is that there are source effects there, and that
Sure.
and that the Fermi bound is relatively reliable. I mean, it's just one photon, but if you took the second photon, the second highest photon, you wouldn't get a very different bound.
Yeah, but you may have a theoretical explanation that it is there is a cosmological quantum gravity scale which is dependent on the era because of the details of the model. You may have a void of defect. Depends.
So actually I had a quick question
Sure.
of understanding. So because you keep saying that the density of the defects might be redshift dependent, and then you keep talking about a void. So I'm wondering, you mean it's a spatial inhomogeneity,
Yes.
or it's
Yes. Suddenly the defects get, when they are going, okay, at redshifts around 1, they may get a void of this defect, so the density of the defects
yeah, but it's as a function of z and not
as function of z.
Or, so
And of the
it's
bulk.
not in a particular
Not in a
angular
particular direction.
Not in a particular direction, because you have to
so
think
no,
of the,
I got confused by how you refer to
Yeah,
void.
because if you say void, it looks like it's anisotropic.
no, void
Yeah,
in
yeah,
the
right, right,
it is anisotropic, but in the bulk.
Yeah, but
It's
how,
void in the
how
bulk.
plausible is this? I mean, you have these things and they dilute. I mean, what else can they do?
They dilute where?
Well,
Not in the bulk.
space form.
Not in the bulk. They dilute.
So the different photons are traveling to different distances.
Yeah.
Ones come from farther away and ones
Yeah, yeah.
Yeah, but
So the ones that are closer are feeling all the stuff. The ones that are long
And they feel a void.
travel a long distance without feeling.
It's an artificial model. I'm not saying that this is a physical model.
Let's say, Nick, it's difficult to see within this motivation for your model why at z equal 1 there should be this sudden decrease of the density.
Because of the deceleration, acceleration, because all these things, because suddenly you get a,
Because of
you
the
get, because they
concept of
accelerate,
energy.
because they, because they attract gravitationally, and that's why they cause the
But then
acceleration.
we are at the center of the we happen to be at the center of this gas of effects.
If you like.
So this is the last question,
This
Joao.
was exactly the question I asked in the beginning of talking to mavromatos, which is, it would be really nice to have, actually, if the metric is going to depend on the energy, it would be nice to know an active
A what? Sorry?
You have something like the Einstein's equation,
Yeah.
which would actually tell you whether your voice or not, whether the cosmological solution is useful or not. And as far as I know, you're just basically postulating a solution to an equation that doesn't exist.
No.
It's kind of, you don't actually have an equation, you have the equivalent of the Einstein's equation.
But the Einstein's equation is a low energy effective action. These are string theories, these are defects. So
we have a high energy version of the Einstein equation.
here,
Would you like to?
you have in the last transparency when your metric is Finsler, so the Einstein equation is affected by writing. You have particle production, so it's a bit more complicated. That's your method. In the effects, the indirect effects here. The Friedman equation, I have you have these extra terms. I have them in the paper. I didn't show them there. You have extra terms of the Einstein. So you have the R, the standard Einstein terms, plus these offset terms that describe the interaction with the
Those
defect.
terms are, so it's basically like a particle production.
Yes, with a source. That's, if you like, at the level of the density of matter, that's how they act. And this sigma square are the
So
fluctuations.
you're plugging everything into the right-hand side of things.
I put everything on the right hand side.
Then you have a theory with the ground fields.
Yes. Which
So
is
that
like
means
the
not
recoil is a background. Yeah. No, it's not background independent. It can't be.
Okay.
But it is a background independent because this is a solution of string theory, you know what I mean? So it's like any other string theory that you do.
Well, you're getting on a slippery, okay.
Well, I'm sorry, but yeah, no one knows what their theory is, right? So, but it's a background. It's a background independent thing.
Okay, so then we have the coffee break and we're running behind a little bit, so we will continue at 4. And thanks again to Nick.
Thank you.